So in this talk, we will discuss neuromorphic technology for brain-computer interfaces. My name is Yao-Hong Liu. I'm scientific director in IMEC Netherlands. I'm also the principal investigator of the ERC-granted project Intranet of Neurons. Our brain is the most complicated object in the universe. It has up to 80 billions of neurons, which is comparable to the planets in our galaxy. And each neuron has up to 1,000 connections to other neurons. This lead to an unimaginable interconnected network. Our brain gives us a feeling that we are very unique individual, but we have very little idea how our brain functions. Over the decades, neuroscientists, researchers, engineers try to develop neurotechnology in order to understand better our brain. One of these technology is based on imaging approach, like fMRI. It provides a colorful image to indicate the active area of the brain. This image technology gives us a macro view of how the brain functions, but it does not provide much more detail. I like to use the analogy of the using an advanced telescope to watch the universe. You will know something happened somewhere there, but you don't know exactly what happened there. In order to know more detail, we can send a spacecraft, for example, like we sent Perseverance rovers to the surface of Mars, and it would take a lot of pictures and then send it back to the Earth for detailed analysis. Similarly, neuroscientists and engineers also develop this kind of intra-cortical neural sensors to be placed on the surface or inside the cortical area. This intracortical sensor can sense the electrical signal firing from the neuron. One of the FDA-approved intracortical sensor is this Utah array that has 100 channels on these sensors, like needles as shown here. So these intracortical sensors also enable another new technology called brain-computer interfaces. The brain-computer interfaces, it will acquire the brain signal with these intracortical neurosensors. After decoding, our mind can interact with external machines or computers. This is a very powerful technology that can potentially help many people with disabilities. For example, this woman in this video who lost the control of her limbs by decoding the brain signal, she's able to grasp the cup to drink again. And you can see this is a big box on top of her head is a previous generation of the brain-computer interfaces. And this brain-computer interfaces technology is continuously evolving. And I would like to talk about the future trends of the brain-computer interfaces. The first trend is to scale up. We want to decode more neurons. As in the BrainGate project from DARPA, it shows that by decoding 100 neurons, we are able to perform simple tasks like grasping. We want to do more sophisticated hand functions, hand activities. For example, tying shoelace. This will need to decode more than 10,000 neurons. And furthermore, for the full body with exoskeleton, controlling exoskeleton, we will need at least 100,000 of neurons. So in order to, there are several two approaches to increase the access to more neurons. One is by increasing the density of the neural sensors. This plot shows the survey from Stevenson Lab. They provide the data that is starting from the 1950s of the data showing the neurons, number of neurons that can be simultaneously recorded. And you can see the number is almost is doubling almost every 6 years. This is like a neurotechnology version of Moore's law. And the highest number of neurons that can be simultaneously recorded by the intra-cortical neurosensors is from IMAX neuropixels, which leverages the advanced semiconductor technology to squeeze many electrodes, sensing electrodes in a very small needle. Another approach to increase the number of the to access more neurons is to distribute the neuroprobes spatially in different areas of the brains. This is also showing in many recent neuroscience study that these probes, neuroprobes, high-density neuroprobes are distributed across the different brain area in order to study the correlation of them. So on one hand, we want to increase the number of neurons that can be accessed. The second trend is that we also want to minimize the invasiveness. This means that this implant has to be wireless, has to be smaller, such that it does not cause large invasiveness. So as shown in the earlier this figure, the earlier generation of the brain-computer interface is based on this head-mount stage with a long wire connected to a computer. A recent version of this brain-computer interface is becoming smaller and wireless, as shown here. But still, it's penetrating the skin and skull to connect to the cortex sensors. Recently, the star company Neuralink from Elon Musk, they present a new brain-computer interfaces that by replacing small part of the skull bone with a smartwatch-like implant, so they can be fully implant below the skin. This further reduce the risk of infection. The last trend is the closing loop capability. The closing loop capability means that the brain-computer interfaces has a capability to not only provide sensing the brain activities, also decode them to get the useful information such that it knows that when to perform stimulation to achieve certain therapeutic purpose. And currently, most of this closing loop capability is done by transmitting out of the data wirelessly to a remote stationary computer for neural processing. And transmitting this data will consume huge amount of energy, at least 100 picojoule per bits. So you can imagine this approach is very energy consuming. It also has a long latency by sending out data to further away. It also has a potential privacy issue. Of course, we can also, lots of research also done that perform this closing loop directly in the implant by having this implantable neural processor. But due to the limited computation resource, this type of implant neural processor has limited accuracy. It also requires frequent calibration, rely on the remote stationary neural processor. Another limitation is that it is also lack of flexibility. So this is similar to a problem in the conventional IoT network. it's a trade-off between the edge computation versus communication. So this is also the aim of my ERC project, Intranet of Neurons. We are aiming to develop a neural data telemetry that can enable large-scale, minimum invasive, and bidirectional brain-computer interfaces. And we want to be inspired from the biology. So now I would like to talk about how do we inspire from the biology to design a better neural data telemetry for the intra-cortical brain-computer interfaces. So first, we would like to understand what is the requirements, the data rate. So as we mentioned previously, we want to have a high density intracortical neurosensors. So let's assume that each neurosensors has 1,000 channels, 1,000 electrodes. And in order to get the full spike features, which is very sparse signal, we have to sample at a relatively high frame rate, up to 25 kilohertz. It's a simple math. We can get, we'll need up to 250 megabit per second data rate. To give you an idea, this is roughly the data rate similar to a Wi-Fi device they can achieve. And you can imagine that now if we want to achieve similar data rate in implants, it's going to be very challenging. But let's take a look how we can be inspired from our body. So one example is our retina. Our retina is equivalent to a high resolution camera that has up to 500 megapixels of resolution. But the question is that how our retina being able to transfer the data from our eye to the back of our cortex, the visual cortex, via this very tiny optic nerve. Apparently that consumes very little power, and it also has a very small area, small volume. So how does it do? Are we processing the neural data in the correct way? Apparently, this question has only been studied in 15 years ago from ETH group. They have this bio-inspired camera, also called dynamic vision sensor. So instead of taking the image frame by frame with a high resolution, this dynamic vision sensors only provides outputs when there are changes. So you will get something similar image like this. This is very similar to what our retina outputs. But our brain visual cortex has no problem to reconstruct them back to a very high resolution image. So this is done by this kind of circuits, integrated circuits with an in-pixel event generation that perform so-called delta sampling. So I would like to explain a bit more about operation of this delta sampling. On the left upper side, I show the conventional frame-based sampling. In this frame-based sampling, we have a fixed sampling clock, and each clock they will capture a frame with a high resolution, capture the data with high resolution. On the other hand, for the delta sampling, it does not have a fixed sampling rate. Instead, it only gives outputs when it changes over certain step. So this is the example of the delta sampling with the neural signal. So neural signal is very sparse. Most of the time is quiet, and you only have a signal when there's a neuron firing. So with this delta sampling, we are able to provide very good compression ratio from 100 to 1000x. At the same time, after reconstruction, it has still very, it can reconstruct back to a very high resolution neural signals without any distortion. So now, how can we perform transmission of this event data? So let's take a look at this graph. So in each channel of this intra-cortical neural sensors, we will perform this delta sampling to generate these asynchronous events at the outputs. And then before wireless transmission, we use time multiplexing or arbitration to resolve any event timing confliction. And then similar to many neuromorphic systems, we use address event representation. In this case, it's a serial format. We attach which channel address is sending these events. And then also we add Manchester coding and ternary coding in order to optimize the wireless link quality. And here is the waveform showing from our recent publication. Here is the spike of the neuron firing, and then here is the delta sampling, up and down signal, and then finally here is the ternary coded transmitter output. So what is the next step? As mentioned previously, we also want to distribute it, these wireless intracortical neural sensors. And these distributed wireless sensors, event-based sensors will produce asynchronous events wirelessly. And then there will be a receiver that pick up all of these asynchronous events from the air. So if you put a proper weight of each of the events from different wireless intracortical sensors, and then you sum them together, perform integration and fire, actually it can be also become a wireless version of spiking neural network. The only difference is that in the air, we have to, it's more difficult to handle the event collision in the air because we cannot control the time when does it arrives. So we will need to process them in the wireless network level. So that will be our next ongoing research. Okay, after discussing the data communication part, I would like to talk about the data processing part. In order to know how in order to perform data processing, we also need to know better what is the intracortical neurosensing data. Here shows examples, one example of the intracortical neurosensing signal, which represent the extracellular membrane potential. So each channel, because there is the density of the neural probe is very high, so it's very likely that each channel is possible to pick up neural firing, spike firing from different neurons. For example, this is a one firing from one neuron, and this might be a firing from another neuron, yet another neuron. So how can we know that which firing is from which neurons? This process we call spike sorting. This is also a very important step in the decoding the neural signal. In this slide, I would like to talk about how what is the typical procedure of performing spike sorting. What is the steps? So first, we use the intracortical neurosensors to record the data shown here. And we try to detect when the spikes happen, when the neuron is firing. And then by extracting their features, for example, and then we do the feature extraction to extract their feature, for example, the amplitude of the spike, the width of spike, etc. And then we perform clustering to create a template such that we can use to perform classification. With this classification, we are able to know that this firing is from which neurons. Then we can extract the firing pattern. Ideally, we want to transmit this sorted spike events because this is it says a lowest data rate and also with meaningful information. However, it requires very high computation requirements and is still not yet feasible to be implemented inside a very miniaturized implant, especially with a high sensing channels. On the other hand, we also don't want to transmit the raw data because it contains too much information and then they will drain very fast the battery life. So actually, if you look at this process, the most compute demanding part is this clustering and classification because the template need to be created and also storage. So if we can just transmit the data right before this clustering and classification by transmit just the spike features, we can already reduce a lot of data, and at the same time, its computation requirement is still acceptable. And this work further explore this approach and even combine with the delta sampling. So this is the waveform this is a firing waveform, and here is the delta sampling output. So by extracting the temporal event features from this delta sampling, in this case, they propose to have 4 temporal features, which include minimum, maximum, and also the minimum slope of decreasing and minimum slope of the increasing. These are 4 temporal event features. They are already able to achieve very good sorting accuracy. And compared to conventional principal component analysis, this can, which is already low, reducing the features, this can further reduce the feature extraction complexity by another 100x. We also explore this temporal feature extraction with neuromorphic spike in neural network. So as shown here, again, this is action potential. This is spike firing waveform with a depolarization, repolarization, and hyperpolarization phase. And here is the delta sampling result with a recurrent spike in neural network with approximately 100 neurons. We are able to extract the timing of these 3 phases, and it only consumes less than 10 microwatts energy. Okay, now I would like to talk about another type of neural decoding, especially for motor BCI, motor brain-computer interfaces. The neurons in the motor cortex has a very interesting property that their firing is very similar. The firing pattern is very similar. So typically for this motor BCI, there's no specific benefit to perform extra spike sorting. In this case, we can just directly use a thresholding to get the spike timing information and then directly perform decoding. And most of the neuroscience evaluate this decoding performance by using so-called center-out task. The center-out task is that by decoding the recorded neural signal, it controls the computer cursor to move between points on the screen. And by evaluate the accuracy of moving to the right points and also the variation of the trajectory, we are able to analyze the decoding performance. The state-of-the-art decoding is based on Kalman filter. It can achieve up to 99% of the accuracy, but at the same time, it's also very hardware demanding. So recently from Stanford University, they explore using the neuromorphic spike in neural network, which is much more inefficient to replace the hardware demanding Kalman filter. So their study shows that if we can implement a spike in neural network with up to 2,000 neurons we will have comparable performance as a common filter. And the lower part also shows the center out trajectory, and you can see the spike neural network version of decoder can also achieve a very good trajectory. Furthermore, in 2016, Italian Institute of Technology, they also implement this spike neural network for neurodecoding. So by using only 256 neurons spike neural network, they are able to decode the signal with a good trajectory, and even they have a self-learning capability. The area of the ASIC is a 50 millimeter square, which is still relatively large for implantable devices, but this will progress in the future technology. Okay, now I would like to conclude my presentation. So in the first part, I give a short introduction about the brain-computer interfaces and its importance to help the people with disabilities. In the second part, I talk about 3 important trends in the future brain-computer interfaces. One is the largest, higher number of channels. Second is that to have a minimum invasiveness, and the third one is to be able to close loop. And the third part, I introduced several bio-inspired neural data telemetry and processing technology. So here I would like to conclude my presentation here with a short short discussion. So from 1950s, we have a first brain-computer interface technology that is with a micro-electrode arrays to first time be able to record the brain signal. And this helped to advance neuroscience in the coming decades. With the advance of neuroscience, we also have a new neuromorphic engineering technology that is starting from roughly year 2000s, starting from Georgia Tech, they built a neuromorphic computer. And now we want to, based on this neuromorphic engineering, to further improve the efficiency and performance of these brain-computer interfaces. And we hope that there will be the next step with these brain-inspired brain-computer interfaces, we can further advance neuroscience. Thank you.